Before we get started with Calc 2, we did a little algebra review and trig review, and now let's do some Calculus 1 review. Now when we talk about Calculus 1 review, it's important that we know our basic derivatives. So let's go ahead and write our derivatives rules that we should have memorized here. So the derivative of the sine of u is equal to the cosine of u times the derivative of u. And I'll write derivatives as u primes for this particular example. So this is the chain rule. Let's go ahead and do the same thing for cosine and tangent. And again, these should be memorized. The derivative of cosine is a negative sine of u, u prime. And we'll do tangent as well. The derivative of tangent of u is secant squared of u, u prime. Now, depending on where you took Calc 1 or the instructor you had, they might have used notations like d du to mean the same thing. So u prime and d du are the same. And I'll do some examples so you get used to that notation. Now let's keep looking at this. Let's look at our reciprocals as well. The reciprocal of sine is cosecant, so the derivative with respect to x of cosecant u is equal to negative cosecant u cotangent u, u prime. That's the chain rule. The reciprocal of cosine is secant. The derivative of secant u is secant u tangent u, u prime. The derivative of cotangent is negative cosecant squared of u, u prime. Okay, so those are the derivatives that you should know. And then let's go ahead and look at the antiderivatives as well. Now when we talk about antiderivatives, basically what we're doing is we're talking about if we integrate what we got for our derivative, I should get the original function back. So that's what I'm saying when we talk about antiderivatives. So let's write those out. So the integral of the cosine of u du is equal to the sine of u plus c. Now a couple things to look out for. These are indefinite integrals, so that's why we have the plus c on here. So again, on this one, what I did is I integrated what we got for our derivative result, and I get the original back. So these are called antiderivatives. So the integral of the sine of u du is negative cosine of u plus c. So that came from this one right here. When I integrate sine, notice I have this negative left over, and so I move that across. Okay, our next one would be the integral of secant squared of u du is equal to tangent of u plus c. Then I have the integral of cosecant u cotangent u du is equal to negative cosecant u plus c. And those are over here, so I'm integrating this side, getting my cosecant u. So if you know, to me, if you know this, if you know your basic trig derivatives, you know your antiderivatives as well. Let's look at our next one. If I integrate secant u tangent u du, I will get secant u plus c back. Okay, and then our last one here, the integral of cosecant squared of u du is equal to negative cotangent u plus c. So I should have, these are some basic things that would be very, very helpful if you had them memorized, because we use them so often. And now we're going to start using them in more complicated integrals. So if I have these basic ones memorized, it'll make the more complicated ones that much easier. There's a few trig identities that are helpful to know. I wouldn't expect that you'd have trig identities all memorized, but some that I would expect that you would know are your Pythagorean identities. The Pythagorean identities are sine squared plus cosine squared equals 1. So when we talk about that, we always include the angle. So sine squared of theta plus cosine squared of theta equals 1. We also have 1 plus tangent squared theta is equal to secant squared theta. And 1 plus cotangent squared theta is equal to cosecant squared of theta. So the Pythagorean identities, again, are something that I would expect that you would know as well. They come up a lot. We used them a lot in trig, and we'll be using them here as well. A couple of formulas that I wouldn't expect that you would know that would be on a formula sheet and I'll be providing a formula sheet for every exam because there's a lot of trig identities and some things that I wouldn't expect that you would have memorized. One of them would be the sine of 2 theta is equal to 2 sine theta cosine theta. Okay, and then we could also look at substitutions for cosine squared of theta is equal to 1 plus cosine of 2 theta all over 2. And we have a similar formula for sine squared. So that would be 1 minus cosine of 2 theta all over 2. Okay, now we also have some other things that I'd include on the formula sheet, such as some integral forms for inverse trig functions. So if you have an integral of the form 1 over the square root of a squared minus u squared du, that would look like the inverse sine of u over a plus c. We'll also have one for inverse tangent that would look like 1 over a squared plus u squared du, and that integrates into 1 over a inverse tangent of u over a plus c. And then let's look at another one. This one doesn't show up as often, but I'm going to throw it on here. I wouldn't expect you to memorize this. So if I have something of this form, that's going to be an inverse secant. So 1 over a inverse secant absolute value of u over a plus c. Mostly these two are the ones that we end up using a lot, but this does show up once in a while, so I want to make sure that I include it. I will also include on this list the integral of secant, and we might end up showing how this integrates to this formula at some point because it does show up quite a bit. So the integral of secant u is natural log absolute value of secant u plus tangent u plus c. Now we haven't talked much about logs, so we're going to be talking about exponentials and logs, but this does show up, and I'll show you how to get to this result at some point. It does show up, but I want to just put that on the formula sheet for now to use as something that we can just refer to. So the integral of cosecant, as you might guess, is negative natural log absolute value cosecant u plus cotangent u plus c. So there's going to be some other things that we throw on here as we work and we think, oh, we needed that strange trig identity, but this is kind of a good start. So again, you need to make sure that you have your basic derivatives and antiderivatives memorized, as well as your Pythagorean identities. And on your formula sheet, I'll give you some things like this, and we'll add to this formula sheet as well. So what we want to do is just start integrating, practicing integrating to kind of get back in the groove of things. So there's basic integrals. We know our power rules, so if we integrated something like x squared dx, I would get x to the third over 3 plus c. This is called the power rule. So when I have a power, you add 1 to the exponent and divide by the sum. And you can check your answers. So if I integrated this, I would get back to my x squared. I'd get back to what I have here called my integrand. So that's a super basic super basic integral. So let's start looking at some basic substitutions. So some basic substitutions would be something like 2x plus 3 to the fourth dx. Well, I could multiply this out 4 times, but I don't want to do that. That's a lot of extra work here. So what I'm going to do is a u substitution. And again, depending on the instructor that you have, the notation might be slightly different. So I'm going to show you how I look at this, and if you have a different way of doing it or a different notation that you prefer, that's fine as long as you show your work. So the derivative of 2x plus 3, the derivative of 2x is 2, the derivative of 3 is 0, so the derivative of 2x plus 3 is 2 dx. So when I look at this, I have the dx, but I need the 2. So here's my 2 and my dx, and then this piece just becomes u. So when I rewrite this, this becomes u to the fourth, and then the 2 dx is du. And now I'm back to my power rule that I was just using over here. So I'd add 1, divide by the sum, and then I make my substitution back in. So remember, u was 2x plus 3. So this is 2x plus 3 to the fifth all over 5 plus c. Okay, so that's a u substitution. Now sometimes I don't have to compensate, or sometimes there's a coefficient I don't need. So this is called compensation. And you can always compensate for a missing constant. And sometimes you might have a constant in the problem that you don't need, and if that's the case, I can pull that out front. Let's go ahead and look at a rational expression. So let's look at x to the fourth. In the denominator we have 9 minus x to the fifth quantity squared dx. So let's use that substitution again. Now when I look at how I did my substitution, notice I had 2x here, and that was to the first power, but when I took my derivative, the power decreased. So when you're choosing your u's, what you want to do is choose highest powers for your first try. Now sometimes when you take a derivative and you're using u substitution, you might try 2 or 3 things before you find the one that works, so don't get discouraged. Now the derivative of 9 minus x to the fifth, the derivative of 9 is 0. The derivative of minus x to the fifth is minus 5x to the fourth dx. Okay. Well, if we look at this, I have the x to the fourth dx right here. What I'm missing is this minus 5. So I'm going to compensate by multiplying by negative 5 on the inside and a negative 1/5 on the outside. And then I go ahead and rewrite. So I have the negative 1/5 on the outside. Now, what ends up happening here, all of this becomes my du. That's why it's called u substitution. We use it all the time. So all of that just became my du. Now in the denominator, what I have here, 9 minus x to the fifth is my u, so this would be 1 over u squared. Okay. Now to integrate this, I can't integrate it as is. I need to flip it up top so I can use that power rule. And so I add 1. So negative 2 plus 1 is negative 1. Divide by the sum. And then we'll simplify. So I have 1 over 5u. So the u flips because of the negative exponent. And then I make my substitution back in. Remember, u from back here was 9 minus x to the fifth. And then my plus c. So every time I have an indefinite integral, don't forget that constant of integration. Okay, that ends up being very important. If we have definite integrals, then we'll end up evaluating these, but for now I'm just going to look at some indefinite integrals. So the more integrals we do, the better we get at them, so let's practice some more. And most of these you've probably already seen at some point in your calculus careers, but you forget. So let's go ahead and practice a few more of these before we get into Calc 2 material. So some of these substitutions can be tricky. I look at this and I'm like, man, there's a lot going on here. This is my highest power though, is the 4. And so what I want to do is try the base. So again, sometimes it's trial and error. So I'm going to look at root x minus 9 as my u. Now when we look at that, I can rewrite this with, instead of radical form, an exponent. And that's easier to take the derivative of. So to take the derivative of x to the 1/2, I bring the 1/2 down and decrease the exponent by 1. And the derivative of minus 9 is 0. So this is my derivative. Now if we rewrite that derivative, that's 1 over 2 square roots of x dx, because I'll flip this negative exponent down. And I have that. It's right here. So that turned out pretty good. So up here I have u to the fourth du, because all of this takes up my du. So all of this is my du. In fact, I don't even need the fraction bar. I can just write that as u to the fourth du. So my substitution, what I have here, all of this is my du. Now notice that this is in the denominator, and it does need to be in the denominator over here as well. So we'd just go ahead and integrate, add 1, divide by the sum using that power rule. And then from the power rule, I can take that substitution back in. So u to the fifth over 5 plus c. Now it's going to come up that you're wondering if these types of problems show up on a test, which they very well could, some review work. How much work do you show? And the answer is the more work the better. So let's go ahead and talk about the last one we just looked at. And for that one, you know, what is relevant work here? Well, the whole thing is I'm choosing my u, I'm showing my du, I'm showing my substitution, my integration, and my conversion back. So if in doubt, show more work instead of less work. And the reason you want to do that is if you have something incorrect, if I can go back through your work, or if let's say you're over in the slide rule getting some help, if you have somebody helping you, they can go back and find where your mistake is. If you don't list any work, then it's really difficult to find the mistake for both somebody who's helping you and also for yourself to go back through and troubleshoot your problems. Okay, here we're going to do another substitution. So here I'm just going to use the argument of my trig function as my u. My du would be a 5 dx then. So again, I don't have the 5, but I do have the dx, so I'm going to multiply by a 5 on the inside, compensate with a 1/5 on the outside. Now the reason I can do this is if I take 1/5 times 5, that's just the same as multiplying by 1, and I have not changed the value of this integral at all. So what I end up with here then is that 1/5 out front, integral cosine of u du. And this is an integral that I have memorized. It's from up at the top of the list there. The integral of the cosine of u is going to be sine of u, and then I make that substitution back in. U is equal to 5x plus c. There it is. Now again, if you want to check this answer, take the derivative of this and you will get this integrand right back. Guaranteed if it's correct. It's a nice way to check your work. Let's look at a little bit more complicated one with trig. Let's look at one that's cosecant 9x, cotangent 9x dx. Now, a lot of times in my math lab, when you're doing your problems, they'll give you a hint for substitution. So they gave us the hint for this one to let u equal 9x. Okay, so if we let u equal 9x, du would be 9 dx. Now looking at this, it doesn't appear that I have a 9. So let's have a look. So there is a 9 inside 45 because 9 times 5 is 45. But if you don't want to worry about that, what I would do is just pull that 45 out front. And then let's set this up. I'm going to say I'm missing a 9. So let's put that 9 in. But I can't just multiply by 9. I have to also divide by 9 on the outside. So when I do that, then I have 45 divided by 9. 9 times 5 is 45, so I have 5 integral. And this is cosecant u, cotangent u, and then my du. Now this will make a nice little antiderivative that we should recognize. So cosecant u, cotangent u du. So again, that du was 9 dx. And here's the 9, and here's the dx, and it came over here to create the du. So if I look at the integral of cosecant u, cotangent u, again, that's a nice little antiderivative that should seem familiar, and that should equal negative cosecant u. And of course I have to drag that 5 along. But my u was 9x, and there's my plus c. So you might say, okay, where did the integral of cosecant cotangent turn into negative cosecant? Well, I'm going to scroll up here real quick. And it's from right here. So I know that the derivative of cosecant is negative cosecant cotangent. So the integral of cosecant cotangent is negative cosecant. Okay, and that comes from right here as well. So this is from knowing those trig derivatives and the trig antiderivatives. Okay, so u substitution is huge. We're going to be using it a lot as we did in Calc 1, and we're going to be using it even more in Calc 2. So let's practice some more of these. Now a lot of times when you're working with your integration techniques, it's trial and error. So if at first your u substitution doesn't work, try again, because you might find something in your next iteration that does work. Now in this particular case for my u substitution, it's always a good start to try the argument of your trig function. So let's let u equal 1 over x, and if I rewrite that, that's x to the negative 1, so when I take my derivative, that's negative x to the negative 2 dx. So again, when I take my derivative, I bring the negative 1 down, decrease the exponent by 1. Now when I rewrite this, I have a negative 1 up top, and then this x to the negative 2 flips into the denominator and becomes positive. So I have that. I have that right here. The only thing I'm missing is this negative. So that's where I'm going to go through and do my compensation. I'm going to multiply by negative on the inside to create this du right here. But I also have to multiply by a negative on the outside because negative times a negative is a positive, and that doesn't change the overall balance of the equation. So all of this becomes my du now. So when I rewrite this, I end up with negative integral sine squared of u, and then negative 1 over x squared dx becomes my du. Now this doesn't look familiar as an antiderivative, but we do have a trig identity that we had on our formula sheet that would be very, very helpful in integrating this. So let's scroll back up and have a look at that. If we look at sine squared of u, I can rewrite it using this identity, 1 minus a cosine of 2 theta over 2. So note, we're going to use the trig identity, sine squared, and I'm going to use u here instead of theta just because that's the variable that we're looking at. That was 1 minus the cosine of 2u all over 2. So this is going to end up being almost like a double substitution. So when we substitute in, remember I have the minus sign out front. Now sine squared is going to become 1 minus the cosine of 2u all over 2 du. Okay? So to integrate here, I'm going to go ahead and pull this constant out front. So I have a negative 1/2 out front, and then I have 1 minus the cosine of 2u du. I'm going to have to do another substitution here, but I think what I'd like to do is to split this up into two separate integrals. So this looked pretty simple or straightforward at the beginning, but it's getting pretty complicated. So let's call this 1 du, and we have to keep track of our u's and our du's because we're about to introduce another variable. Okay, and then I'm going to have minus 1/2 integral negative cosine of 2u du. So all I did is I took this negative 1/2 and I distributed here, and then I separated these into two separate integrals. So this first one is easy enough. That's negative 1/2 u because the integral of a constant is just the constant times u. So that one's done. I'm good there. Now here I have a negative times a negative is a positive cosine of 2u du. Okay, now I have to do another substitution. So here we're going to introduce another variable, and I'm going to call it w, and I'm going to let w equal 2u, so then dw equals 2 du. Okay, now it's important that we keep track and we don't keep using u over and over again, because if I use u again, u is already defined up here to be something else. It was 1 over x. So that's why we're introducing this new variable for substitution. So I can go ahead and rewrite now. So I'm just going to drag this along. I've integrated this. This part's done. Now this part is going to be cosine 2u is w. Now to get my dw though, I needed a 2 du, and I have the du, but I don't have the 2. So I multiply by 2 on the inside, compensate with a 1/2 on the outside. So this 1/2 times 1/2 becomes 1/4. This is a really good one. Okay, so this 2 du becomes dw. Okay, now I'm just going to keep dragging this along. I'm going to wait to substitute back in all at once. Now the integral of cosine, if you recall, was negative sine of w. Okay, so let's look at the integral of cosine. If you don't remember, let's go ahead and pull up that formula sheet. So the integral of cosine, oh I'm sorry, I had it backward. The integral of cosine is a positive sign. Okay, so make sure let's fix that up. And I always should remember that because the derivative of cosine is negative. The integral of cosine is positive. So this is positive cosine, or sorry, positive sine of w Okay, so now I'm ready to do my substitutions. So now let's go backward. What was u? Well, u was way back here at the beginning. So u was 1 over x. So let's make that substitution. Okay, and now w was 2 times u. Okay, so now I can make that other substitution. 2 times u, but u is 1 over x plus c, and then we can clean this up a little bit. So this is equal to negative 1 over 2x plus 1/4 sine of 2x, or sorry, 2 over x. There's a lot going on here. 2 over x plus c. This was really a good one. I really like this one. We got to use the double substitution, but it was pretty straightforward. And I'm going to make a note here. The integral of the cosine of u du is equal to the sine of u. Okay, and then plus c, of course, but this is kind of intermediate work, so we can hold our constants of integration till the end. So that was a really good one. I like that. So again, if you're wondering about how much work to show, this is how much work to show. So that way, let's say you're working along and you have everything right, and then right here at the very end you substitute incorrectly, I would be able to give you credit for all of this correct work up here, and then you just get dinged a couple points down here for that finishing up. But if you don't show any work, if you just skip, let's say you got this part right and then you jump to your answer, then there's no partial credit. So I want to be able to give you lots of partial credit because you're doing good work. So make sure you write it out and explain your good works. Okay, here let's go ahead and look at the integral. We'll get something a little bit easier this time. That one is a pretty long one. Integral of 3 plus 8s ds. Okay, so again we can use a u substitution here. U substitution, I could think about this as being my u, but I think before we even go any further, I want to just go ahead and rewrite this. I'm going to take this from radical form to exponential form. That's exciting. It makes it easier to integrate. So let's look at 3 plus 8s. The derivative of 3 is 0, and the derivative of 8s is 8 ds. So what I'll do is I have the 8, or sorry, I have the ds right here, but I'm missing the 8. And so compensation says I can multiply by an 8 on the inside if I compensate with a 1/8 on the outside, because 8 times 1/8 is 1. So I haven't changed the value of the expression at all. Now the 8 ds becomes my du, and so I have 1/8 integral u to the 1/2 du. So we drag the 1/8 along and I add 1. 1/2 plus 1 is 3/2, and then I divide by the sum, so I'm dividing by 3/2. So let's go ahead and rewrite this. When you divide by a fraction, you multiply by the reciprocal. And then I can simplify this. So 2 goes into 8 4 times. So it looks like I have 1/12 u, which was 3 plus 8s to the 3/2 plus c. So there is my integral. There's my solution. And again, if you wanted to, you could take the derivative of that to check your work. So if you're on a test and you want to check, you could take the derivative. And you'll have plenty of time on your exams to work through the problems, and then also to go back through and double check anything that you need to. Now this one, I want to make sure we're careful how we write this. Sometimes this root can look like a power over here, so I want to be clear this is part of the radical. So first step I'm going to take here is to rewrite this in from radical to exponential notation. So the fifth root would be 1/5 dx. So let's go ahead and get started with our substitution. Again, we're going to try our base here. So u is 25 plus x squared. Du is 2x dx. Okay, I have the x, I need the 2, so I multiply by 2 on the inside, compensate with the 1/2 on the outside, and I have 1/2 integral. Now all of this 25x squared is my u to the 1/5, and then the 2x dx is my du. So now I'm ready to use the power rule. Add 1. 1/5 plus 1 would be 1/5 plus 5/5 is 6/5. divided by 6/5. So I have 1/2. When you divide by a fraction, you multiply by the reciprocal. And then we'll go ahead and clean this up. So this would be 5/12. And then u, we remember, was 25 plus x squared, and this is to the 6/5 plus c. Now if you want to rewrite that in a radical notation, you can, but it's not required at all. I always like doing the integrals with the trig functions. Those are always interesting. Let's look at the integral of sine to the 4th. Our argument of our trig function is x over 3 here, times cosine x over 3. Okay, so now we're getting into some interesting territory. This, you might say, well, let's let u equal x over 3. So let's try that and see where it goes. du would then be 1/3. So if I rewrote everything, I'd have 1/3 on the inside, then I have to compensate with a 3 on the outside. So I'd have 3 integral 1/3 sine to the 4th of u, cosine of u, and then du was the 1/3 times dx, so I can get rid of this now since I have that du, the 1/3 is here now. This doesn't look much better, really. It looks a little better, but not much better. We could do another substitution here. That could work. Or I might try a little bit more complicated of a substitution to see if it could work. So we don't have a guarantee here, but I have a suspicion. I'm going to box this off and think, yeah, this could work. What we would do from here is we'd introduce a new variable, and we'd say w equals sine of u, and then dw would be cosine of u du. So yeah, that would work. We could do that, but I'm just kind of curious about something. What if we did u equals sine of x over 3? Then du would be 1/3 cosine x over 3 dx. Okay, so where does that come from? That's from the chain rule when you're taking derivatives. So the derivative of the sine of u is cosine of u, and then I have to take the derivative of x over 3, which is 1/3. So that's the chain. So if we do that, this piece right here would become u to the 4th, and then this piece is almost my du, but not quite. I'm missing the 1/3. So if I multiply by 1/3 on the inside, I'd compensate with a 3 on the outside. And then this whole piece right here becomes my du. So I kind of like this a little better. It's a little cleaner. I don't have to do that double substitution here. So I'm going to add 1, divide by the sum. So 3u to the 5th over 5. And then make my substitution back in. So my substitution here, u was sine of x over 3. Now I can't write it like this. That would be wrong. The 5th power here, the way I have it written, is on the argument. The 5th power needs to be on the entire value of u. So there's a couple ways that you could write that to make it clear. One way we could write that is sine to the 5th all over 5 plus c. That would be one way. So this is a correct answer. And another way we could write that is 3 and then put the sine of x over 3 in brackets and then raise the entire thing to the 5th power plus c. So either one of these is correct. You can't write it though like this. This is wrong. Okay. Now coming back up over here, this is kind of interesting. If you follow through with this and make that other substitution, you're going to end up exactly in the same spot. Okay, so a couple different ways to do the same integral. I just kind of feel like this one step is the easier way to go. Okay, let's look at another one. These are fun. Okay, let's look at the integral of r squared. And then this would be r cubed over 24 plus 6 to the 7th. Well, we've done quite a few of these now where we start to see some patterns. Let's look at the base of this exponent. And remember, this is r cubed, so when I take the derivative, it's 3r squared, and I have that. I just have to do some compensation. So let's try that. Let's let u equal r cubed over 24 plus 6, and then du would be 3r squared over 24 dr. So when I take my derivative here, I bring the 3 out front, decrease the exponent by 1. Now this can be simplified just a little bit. So here du, 3 goes into 24 8 times, so this is r squared over 8 dr. And I have the r squared. So what I can do is I can divide through by 8 on the inside, and I'd compensate by multiplying by 8 on the outside. So this looks like 8 integral, and then r squared over 8 dr is substituted in for my du. And then this entire r cubed over 24 plus 6 is my u, so that's u to the 7th du. And then I just use my good old power rule, add 1, divide by the sum. The 8's cancel, and I'm just left with u to the 8th here. But u is r cubed over 24 plus 6 to the 8th. And then, of course, we have our plus c, our constant of integration. So don't forget that constant of integration. Okay, I like that one. That was a good one. A good old u substitution. Okay, let's do another. Let's do some trig functions. Okay, so this one is a little bit trickier. Sometimes when you don't see a substitution right away, you have to think about your derivatives. So the derivative of sine is cosine. The derivative of cosine is negative sine. So u's and du's of each other are sines and cosines. But let's kind of rewrite this just a little bit, so it might make it a little bit more clear. I'm going to rewrite this as cosine of 4t plus 4 in brackets quantity squared, just so it's easy to see now that I'm probably going to use this for my u, because this is u squared. Okay, so let's try that. Let's let u equal cosine of 4t plus 4, and then du, the derivative of the cosine is negative sine, so negative sine 4t plus 4. Now I need the derivative of 4t plus 4, which is 4, and this would be dt. So I'm going to rewrite that by pulling that 4 out front. So again, that's the chain rule. So just to review one more time, the derivative of the cosine of u is negative sine of the argument, and then I have to take the derivative of the argument, which is 4. So let's make these substitutions and see where we're at. It looks like to me that we need a negative 4 on the inside to make this work. So if I multiply by a negative 4 on the inside, I have to compensate on the outside with a negative 1/4. And the reason I do that is the 4's cancel, and when the 4's cancel, I've really not, just essentially multiplied by 1, and I haven't changed the value of the integral. So this would be a negative 1/4 integral. Okay, all of this is my du from right here. And that should be a t there, because I haven't substituted in yet, so that's a dt. Okay, so that's a 1 on top and a du, and then the denominator is u squared. So I have a negative 1/4. I'm going to flip that u squared up top, and the reason I'm going to flip it up top is so I can use it as a nice power rule. Now what I can't do is drop my integral sign, so be careful about your integral signs. Sometimes people just drop them, but you can't drop them till you've actually integrated. So using a power rule, I'm going to drag the negative 1/4 along as the constant out front, and I'll add 1, divide by the sum. So this is going to be 1/4 u to the negative 1, which is 1 over 4u. But we know what u is. U is right up here, cosine of 4t plus 4. Now we don't want to write it like this, because then it becomes, is the 4t the argument of cosine, or is it 4t plus 4? It's not clear if we use this notation. So always put parentheses around the arguments of your trig functions. And that is my integral. That is my solution. Okay, let's go ahead and look at a few more. Ooh, this is a good one. This is called change of variable. Now we're going to be learning some new techniques in Calc 2, And there might be a technique that I could use in Calc 2 to solve this, but we have to use Calc 1 techniques since we're reviewing. So this would be x over the square root of x minus 8. So let's go ahead and try a couple things. By now you're probably getting kind of an intuition as what I should be using. So I might look at that and say, let's let u equal x minus 8. Du would be dx. So if I do these substitutions, I have my dx. I can rewrite this as u to the 1/2, and I'm left over with this variable. Okay, so what I'm doing right now isn't working. However, if I look at u equal x minus 8, I could solve this for x and I'd get x equal u plus 8. So if I solve for x, I would go ahead and add 8 across. And then this is why it's called change of variable, because I'm changing my variable over from x's to u. And I can't use a direct substitution because I'm left over with the variable. And when I'm left over with the variable, that's a hint that I should try my change of variable. So in the numerator, in place of x, I'm going to put u plus 8. In the denominator, this is u, the square root of u. So x minus 8 is u, and it's the square root. So I'm going to rewrite that as u to the 1/2. And then du is dx. So change of variable. I tried my substitution, and when I substituted everything in, I got rid of everything, but I was left over with the variable. So the hint there is to solve for that variable and then sub back in. Now I can work with this. What we'll want to do here is separate the numerator. You can always separate the numerator. You can only separate the denominator if it's a single term. Okay, now what I want to do is simplify. So I'm not integrating, I'm still doing the prep work, the algebra work here. So u over u to the 1/2 is u to the positive 1/2. And then here I'd flip that u to the 1/2 that's in the denominator up to the numerator and make it negative. So I haven't integrated, I've just simplified. U over u to the 1/2 is a u to the 1/2 up top. And this one I flip the u to the 1/2 in the denominator up. So let's go ahead and add 1, divide by the sum. 1/2 plus 1 is 3/2 divided by 3/2. Negative 1/2 plus 1 is a positive 1/2 divided by 1/2. So again, when you divide by a fraction, you multiply by the reciprocal. So let's clear those up first. Oh, I'm excited about this one. We're going to be able to simplify this one. We're going to factor out. So when I'm working here at this point, I could rewrite this and factor some things out because I have a 2 that's common. I also have a u to the 1/2 that's common. It's not necessary, but it's fun. But let's make the substitution back in first, and then we'll make that. Oh, I love this one. Okay, 3/2. So I substituted in for u. Now we could be done here. So this could be our answer. But I want to give you a heads up. We are going to start evaluating these, meaning plugging in and evaluating them at particular points. And a lot of times it's nice to be able to simplify these a lot first. So this is just kind of a fun extra step. So if you're happy with this answer, you can fast forward or go get a drink, and when you come back, we'll have showed you how to factor this. So we're going to factor this solution to make it look a little bit nicer. So a couple quick things. I could factor out a 2 because there's a 2 common here and here. I could also find a common denominator. In fact, I think I want to. Let's do that. So if we have 2/3, the common denominator is 3. So here this would be 6/3 then. So all I did is I took 2 and I said, okay, I need a denominator here of 3, so I multiplied top and bottom by 3. So now I have a 2 and a 3 that I can pull out front. So this is 2/3, and then I also have an x minus 8 in both of these that I could pull out. But the question is how many of these x minus 8s could I pull out? Well, I can pull out an x minus 8 to the 1/2. That's what I can pull out. So let's think about that. So let's make a little side note here. What if I had an expression, let's say like x cubed plus x squared, and I said factor completely? Well, the greatest common factor here would be an x to the second. So even though we say greatest common factor, the most I can pull out is the x squared. Okay, so if I pulled out that x squared, I'd be left with x plus 1. Okay, so that's what we're doing here, is we're pulling out that lower power between these two. So I pulled the 2/3 out already. I factored out the 2/3. I factored out x minus 8 to the 1/2. So now I have to figure out what's left. Well, what's left is x minus 8 to the first. Now if you're wondering where that came from, if I factor out a 1/2, I have to subtract the 1/2 here. 3/2 minus 1/2 is 2/2, which is 1. Okay, and then over here, I factored out a 2/3, so I just have a 3 remaining. And then the x minus 8 to the 1/2 is already factored out front. So this is some fun factoring. Okay, so let's keep simplifying. So this is 2/3 x minus 8 to the 1/2. And then inside these brackets, x minus 8 plus 3 would be x minus 5 plus c. Now, this is a solution as well. I like this solution better because when I want to evaluate this now, I'm just evaluating a single term instead of a two-term. So that's one good thing about it, and also it was fun to do. So that's a good enough reason to keep factoring and simplifying. Lots of algebra there. Okay, let's go ahead and look at another example here. And again, I better go back a little bit. So this is a fine answer. It is a correct answer. This is just another form of that where it's been simplified quite a bit. And when we were working with definite integrals, it would be easier to evaluate, but either one is correct. So I don't want you to think you have to get to that solution. It's just sometimes an easier solution to work with depending on what you're working on. Okay, let's look at another one. Whoa, I just saw something when I was scrolling. I think I made a mistake. Hopefully you guys caught it when I was working. When I flipped this 1/2 and I flipped it up top, I didn't include the 8. So this should be a 16 right here. So let me make that correction. I'm going to put it in red so we see where that correction takes place. And then right here, that would also be a 16. So again, my mistake was, and again, it's easy to find because I showed a lot of work. This 8 was here, and when I flipped this, I just flipped it up and said it was 2, and I forgot to multiply by the 8. So there's my 16 here. Now coming down here then, that effect would be, we're trying to find a common denominator. So I put this over 3, so I multiply top and bottom by 3, and that would actually become a 48. Okay, so this would become a 48 right here. 16 times 3 is 48. Okay, so then when I pull out a 2, half of 48 is 24. And there's a 24 right there. Okay, and this comes from 2 times 24 is that 48. Now when I combine these, x minus 8 plus 24, 24 minus 8 is 16. Okay, so this is correct. This is corrected now. And I just caught that when I was scrolling, and I thought, wait, what happened to that 8? And so I have fixed it up. So again, another way to make sure you're showing your work. The more work you show, the better, so you can find those types of errors. So far we've been doing all indefinite integrals. I'd like to look at some definite integrals as well, so we can get used to evaluating some of these integrals. So we're taking the integral from 0 to 5. These are called our limits of integration. And what I do is I go ahead and integrate as usual, and then at the very end I kind of deal with these. So drag them along, don't forget them. Sometimes I need to change them as well. So to integrate this particular problem, I would have to let u equal y plus 4, and then du is dy. Well, I have all of that, but when I make that substitution, I have two ways that I can look at this. So one way, y plus 4 is my u, so this would be u to the 1/2 du. Now what do I do with my limits of integration? Well, I have two options. I have option A and I have option B. So one of them is that you could just drop them and then put them in later, but it would be wrong for me to write 0 to 5 here because 0 to 5 are values that are y. So these are y values. Okay, now if I write them over here, it's implied that they're now u values. So this would be incorrect to do this. So I do not write this because these are values of 0 and 5 are values of y, not u. So one way I could work around that is I could just drop them and then put them back in later. Or another option is I could change them. So right here, if I know y is equal to 0, that would mean u is equal to 0 plus 4, or u is equal to 4. So I could change my limits of integration and say, oh, I'm going to make u equal 4 now, in place of the y equals 0. And then my upper limit of integration, y equal 5, I would plug that in here and say, oh, that's 5 plus 4 for my u, then u would equal 9. So I could change my limits of integration as well. Now, whenever you do that, it's a good idea to substitute in or show what your new variable is. Like I said, this is incorrect up here, just to stick in the 0 and the 5, because I would assume that the 0 and 5 were used now, and they're not. So from here, I'd add 1, divide by the sum. 1/2 plus 1 is 3/2, divided by 3/2 is equal to 2/3 u to the 3/2. Okay, now remember that these are in terms of u now. So when I look at 2/3 u to the 3/2, I can actually evaluate this from u equal 4 to u equal 9. I don't have to go back to y's because I've already changed my limits of integration. So let's go ahead and have a look at that. That would be 2/3 out front. I'm going to pull my coefficients out front. This would be 9 to the 3/2 minus 4 to the 3/2. Okay, so let's simplify. Now 9 to the 3/2, I have this exponent. The 3 is a power and the 2 is the root. So I'm going to show this step by step here. I could rewrite this as 9 to the 1/2 to the 3rd power minus 4 to the 1/2 to the 3rd power. And the exponent of 1/2 means square root. So the square root of 9 is 3, so this would be 3 cubed. The square root of 4 is 2, so this would be 2 cubed. So this is 2/3. 3 cubed is 27, 2 cubed is 8. Now 27 minus 8 is 19, so this is 38 over 3. So 38/3 is my answer here. Okay, now I could have done this another way. So I'm going to show you the other way. So this is what not to do. Don't do this. B works if I change my limits of integration, but I could have also done a third way. I'm going to put it over here. This is getting a little messy. As I could have rewritten this, the integral of u to the 1/2 to u, and just dropped my limits of integration, and then put them back in later. Now the problem with that is sometimes you'll forget to do that. So my preference would be B, change the limits of integration if possible, and then you don't have to make that substitution back. But let's see how this works. So I'm going to add 1, divide by the sum. So this is 2/3, I'm sorry, that's 3/2. I was thinking ahead here. So add 1, I'd have 3/2 divided by 2/3. 3/2. I have to stop thinking ahead. So then this is 2/3 u to the 3/2. But I know that my u was, back up here, my u was y plus 4. So this is y plus 4 to the 3/2. And now I'm going to reintroduce my limits of integration. And my limits of integration for this problem were 0 and 5 in terms of y. So now I'm going to reintroduce those. So y equals 0 to y equal 5. So now I reintroduce those at the end. So again, I'm going to pull that 2/3 out front, and then I'll substitute in. So I'm going to put in the 5 first. So 5 plus 4 to the 3/2 minus 0 plus 4 to the 3/2. So 2/3 out front. 5 plus 4 is 9 to the 3/2. 0 plus 4 is 4 to the 3/2. Now this should look familiar. That's what we had right here. Okay, so you're going to end up in the same spot, just a different way to get there. So 2/3, and then just like we did up above, the square root of 9, so this means square root. The square root of 9 is 3, 3 cubed is 27. If you want to rewrite that, you could. So this would be 9 to the 1/2 cubed minus 4 to the 1/2 cubed. So 2/3 out front. 9 to the 1/2 is 3. So this piece is 3. 9 to the 1/2 means square root of 9 to the 3rd power there now. And then here this would be 2 cubed. 3 cubed is 27. 2 cubed is 8. 27 minus 8 is 19, so this would be 38/3. So we get the same answer, just a different route. So you can kind of decide which one you like better. And of course, you already know what I'm going to say is all that matters really is that you show your work. So the more work you show, the better. Okay, so I'm going to do one last integral. This is getting pretty long, but I want to make sure I show you a lot of detailed work. So that way when you run into some of these, that you have all the steps you need to be able to solve them correctly. So this is cosine to the -9 2x sine 2x. Now I don't want you to look at this and say, oh, this must be inverse cosine. It isn't. This is kind of a different notation. It didn't used to be a common notation, but I see it more and more now. So I would like to pull that out and rewrite it just a little differently so we don't get that confused with an inverse trig function. This will be exciting. Okay, so now I have this cosine and sine and sine are u du's of each other. So I need to choose a u, and so let's say I choose u to be sine of 2x, du would be cosine of 2x, and I have it, but I don't have a way to work with du to a -9. I could work with the u to the -9 though, so let's try that. Let's let u equal cosine of 2x, and then du would be a negative sine of 2x times 2 dx. Now the 2 comes into play here because I have to take the derivative of the cosine is negative sine of u. The derivative of 2x is 2. It's our chain rule. So I'm missing, it looks like a negative and a 2 up here. So I'm going to multiply by a -2 on the inside, compensate with a -1/2 on the outside. So when I rewrite this, I have a -1/2 on the outside. And then this piece becomes u to the -9. And then all of this -2 sine 2x dx becomes my du. So this looks a lot nicer. Now at this point, I either drop my limits of integration or I change them. So on the last one I changed them. This one I'm just going to drop them and remember to put them back in later. But that's the key, don't forget. So I'm going to add 1. So that's u to the -8 divided by -8. Okay, so that would be negative times a negative is a positive. 1 over 16 u to the 8th. So before I can evaluate this though, because remember my limits of integration are in terms of x up here, I need to get this back in terms of x. So u is cosine of 2x. Now I can evaluate this from 0 to pi over 6. So this is going to look like a 1/16 out front. I'm going to pull that constant out front. 1 over cosine of 2 times pi over 6. So that's my upper minus my lower. Oh, it's nice to work with trig functions. And of course you have your unit circle memorized. So these will be easy to evaluate. 2 pi over 6 is the same as pi over 3. And then 2 times 0 is 0, and this is the cosine of 0. Okay, so let's go ahead and finish this off. The cosine of pi over 3 is where we want to start. But I see this 8 again, and maybe if I can't see 8s or something today. So this is u to the 8. I needed to have that right here. So that's going to get some big numbers here. So this exponent came from right here. I just forgot to copy it down. And again, if you show your work, those are easy to find. So the cosine of pi over 3. Okay, we have our unit circle memorized. The cosine of pi over 3 is 1/2. And again, this is to the 8th power minus cosine of 0 is 1, and this is 1 to the 8th power. Okay, so let's go ahead and simplify this. So when you divide by a fraction, you multiply by the reciprocal. So this is 1 over 2 to the 8th. Sorry, 1 over 1 over 2 to the 8th minus 1, because 1 to the 8th is just 1. Okay, so when I flip this up top, I get 2 to the 8th minus 1. Okay, so 2 to the 8th. So I'm going to double 2 8 times. So 2, 4, 8, 16, 32, 64, 128, 256. So this is 256 minus 1 all over 16, which is going to be 255 over 16. Okay, so don't drop your 8s, I guess, is my big rule to remember today. So hopefully this has been a nice review of your Calc 1 techniques, and also some trig and some trig identities, some trig integrals, and evaluating things using the unit circle. The key is to do more integrals. So I guess if you're ever bored sometime, go ahead and crack open your book and try some of your Calc 1 integrals, and it's going to give you a lot of good practice, because we're going to assume that all of these are in place as we're working through Calc 2. So if you ever have any questions, feel free to let me know. You can stop by my office, you can join my online office hours, you could send me a screenshot and remind of the question that you're working on, and I'd be happy to send a screenshot back of my work or finding errors. But again, the more work you show, the better. That way I can easily go through and find any mistakes. That slide rule is also open. They're also happy to help. So I hope this was a good review over Calc 1, and our next video we'll be actually starting into Calc 2. Have a great day and good luck.